Hello everyone, welcome to the second lecture of this partial differentiation. In this video I am going to solve some more examples on direct partial differentiation. In previous lecture, in first lecture we have solved some examples on this direct partial differentiation, and also we have seen what is a partial derivative. So please go and check the first lecture, watch it, because each step in mathematics depends on the previous step. Okay, so you must watch first lecture and then come to this second lecture. So let's start this lecture. Let's solve the example on this direct partial differentiation. So here, this is our fifth example. We have to solve. Z is given to us. It is x square plus y square upon x plus y. And then we have to show here dou z upon dou x minus dou z upon dou y whole square is equal to 4 in bracket 1 minus dou z upon dou x minus dou z upon dou y. This we have to prove here. Okay. So first of all, you have to check the given example. What is our given to us? Z is given to us. And in terms of it is given to us x and y. Okay. So it is depending on two variables x and y. Right? So first of all, here we are going to write the given part. So the given is z is equal to x square plus y square upon x plus y. This is our given function. From this, what we can say? Z is depending on x and y. So whenever I differentiate z with respect to x, I have to take its partial derivative, because the dependency of z is on two variables, right? And whenever the function is depending on more than one variable, we have to take their partial derivative. Okay. Now, why I have to find here derivatives of z with respect to x and y? If we see the proof here, there are derivatives of z with respect to x and y. So therefore, I have to differentiate given function with respect to x and y. Okay. So here, differentiate first z with respect to x partially. Okay. Now partially means what? You have to keep y constant when you differentiate z with respect to x. But if you see here, x is present in numerator as well as in denominator also. So what we have to do? We have to use the differentiation rule of u upon v. What is that rule? According to this, you have to first differentiate numerator keeping your denominator constant minus, then differentiate your denominator keeping your numerator constant divided by v square. Okay. So this result we have to use here for the differentiation, because here in z x is present in numerator and in denominator also. Right. So by using this result, I can write the partial derivative of z as z is a function of x and y. So first of all, our denominator is constant. So I can write here x plus y constant. Then derivative of numerator means x square plus y square. Now y is constant with respect to x. So its derivative will be 0. So derivative of x square, it is 2x minus. Now numerator, it is constant, and derivative of denominator, right? Again, the derivative of y with respect to x is constant, so it is 0. So I can write here it is derivative of x is 1. Then divided by denominator square means x plus y whole square. So simplifying this now, what I get if I open the bracket here, multiply by 2x to this bracket. So it is 2x square plus 2xy minus x square minus y square upon x plus y whole square, right? Now here 2x square minus x square means it is only x square plus 2xy minus y square upon x plus y whole square. Say this is our equation 1. So we got here value for dou z by dou x. Now similarly I can find the value for dou z by dou y. So now what I have to do? I have to differentiate z with respect to y partially. Okay. Now differentiating here z with respect to y partially, keeping x constant now this time, right? So here first of all write down the derivative of z with respect to y, that is a partial derivative as it is a function of x and y. Now this is our z. Use the result u upon v because y is present in numerator, in denominator also. So here first of all your denominator is constant. Taking a derivative of numerator, it is 2y minus. Now your numerator is constant. Taking a derivative of denominator with respect to y, it is 1 divided by denominator whole square. Okay. Now simplify again here. So if I multiply by 2y to this bracket, what I get? 2xy plus 2y square minus x square minus y square upon x plus y whole square, right? Now here 2xy as it is plus 2y square minus y square. What I get here? Plus y square minus x square divided by x plus y whole square. Okay. Now I got the derivatives of z with respect to x and with respect to y. Now what I have to do here now for this example, I am going to solve the left hand side and right hand side. So first of all I will solve here left hand side. Okay. And what I have to do? After solving this left hand side and right hand side, both the values are same here that I will show here. Okay. And from that we will say hence proved. Okay. So here first of all consider your left hand side. So consider the left hand side. What it is? Yes, it is dou z upon dou x minus dou z upon dou y whole square. That is equal to putting the values of this dou z upon dou x and dou z upon dou y. So from equation 1 and 2, I can put the values. Put your value for dou z by dou x. It is x square plus 2xy minus y square upon x plus y whole square minus 2xy plus y square minus x square upon x plus y whole square. Okay. Now see here, if we solve this subtraction, okay, your denominator is same. So when your denominator is same, I can do the calculation of numerator, means I can add or subtract the numerator, right? So using that, I can write this left hand side here. Okay. So see here, first of all I am going to write our denominator. What is it? X plus y whole square, right? After writing the denominator, I am now going to solve this numerator, doing the subtraction. Okay. So when I do here subtraction, x square plus 2xy minus y square minus 2xy minus y square plus x square. So I hope you are understanding what will be the remaining part. Okay. So what happens here? X square, 2xy and minus 2xy. This will get cancelled. And x square plus x square, that will be 2x square minus y square and this minus y square. That will be minus 2y square. So what is remaining in numerator? Yes, it is x square means 2x square minus 2y square, right? But if we see there is a square of the term, so we have to write here square, right? And also we have to write the square of this term, okay? Now here, if I take 2 common, I'll get here x square, just a minute. So I will get here minus y square upon x plus y whole square bracket square, right? Now see here, I can use here result a square minus b square. What is the result? A minus b into a plus b. So using that result, I can write x minus y, x plus y upon x plus y whole square bracket square, right? So x plus y get cancelled. What is the remaining term here? Squaring the term as there is a square of bracket. So 2 square, that is 4. Then x minus y whole square upon x plus y whole square. Say this is our equation A, right? Now we have solved here left hand side. Similarly, I'll solve here now right hand side. So consider now the right hand side here. Consider our right hand side. What is our right hand side? Let's check. Yes, this is our right hand side. 4 in bracket 1 minus dou z by dou x minus dou z by dou y. Let's write it. 4 in bracket 1 minus dou z by dou x minus dou z by dou y. Okay. Now here, if I can write this, taking this minus sign common, dou z by dou x plus dou z by dou y, right? I can write it like this also. So here, if I use the values of z with respect to x and z with respect to y and add this together, what I will get? Let's check. Okay. See here, this is the value of z with respect to x, right? And this is a value of z with respect to y. So if I add these two terms together, their denominator is same, right? Means I can add this numerator. So when I add this numerator, what happens? This x square minus x square will get cancelled. This minus y square plus y square will get cancelled. And what is the remaining term then? 2xy plus 2xy. That will be 4xy. Okay. So when I add this together, I will get the term here 4xy upon x plus y whole square. Okay. You can check this addition by solving yourself. Now here, cross multiply this. What I get after cross multiplying the terms? Let's check. X plus y whole square, right? Minus 4xy upon x plus y whole square, right? Now open this bracket. A plus b whole square. What is it? A square plus 2ab plus b square. So according to this result, what I will get here? X square plus 2xy plus y square minus 4xy upon x plus y whole square, right? Now here, if you see 2xy minus 4xy, means what is the remaining term then I'll get here? 4 in bracket x square minus 2xy plus y square upon x plus y whole square, right? And now here I can use the result a square minus 2ab plus b square, that is a minus b whole square. So using that result here, now I'll get the right hand side 4 in bracket x minus y whole square upon x plus y whole square. Let's say this is our equation B. Now you can yourself check from equation A and from equation B. Both the values are same. So I can write here from equation A and equation B, left hand side is equal to right hand side, and hence proved. Okay, so as I told you in previous lecture, if these kind of examples are there, by using a direct partial differentiation you have to show something, then you have to find all the partial derivatives that you required and then check your left hand side and right hand side and show that both the sides are equal. Okay, I hope you understood the example. Let's solve the next example on the same type. So here is our now 6th example on direct partial differentiation. So this is the function here given to us. U is equal to log of x cube plus y cube plus z cube minus 3xyz, and we have to show that dou by dou x plus dou by dou y plus dou by dou z whole square into u is equal to minus 9 upon x plus y plus z whole square. Okay. So first of all, before solving this example, always you have to focus on the question, what you have to show. Okay. So here, what we have to show, if you check your left hand side, all the partial derivatives of, so you can see here all the differential operators with respect to x, y and z. Okay, and these are for u. Right? So I have to differentiate u with respect to x, with respect to y, with respect to z. But here you have to check there is a square of this bracket. So I cannot multiply here by this u directly right now. First of all, I have to open this square of this bracket. Okay? So we all know if there is a square of a term, how we can write it? Yes, we can write it a into a. So similarly, I can write this bracket, right? So see here, to solve this example, first of all, what actually I have to do, I am going to tell you. Okay, so if we check the proof here, left hand side is equal to dou by dou x plus dou by dou y plus dou by dou z whole square into u, right? So what I can write here, it is dou by dou x plus dou by dou y plus dou by dou z into again dou by dou x plus dou by dou y plus dou by dou z, right, into u. Now what I will do here, I will multiply by this u to this first bracket. So what I will get here, yes, dou by dou x plus dou by dou y plus dou by dou z into dou u by dou x plus dou u by dou y plus dou u by dou z. Okay, so now it is clear to me that we have to find all these derivatives of u with respect to x, y and z, right? So finding all these derivatives of u with respect to x, y and z, we have function u. Write down a given part here. U is equal to log of x cube plus y cube plus z cube minus 3xyz. So I hope now it is clear to you what we have to do to solve these kind of examples. First of all, we have to always check what we have to prove here. Okay. Now differentiating u with respect to x first. So here differentiate u with respect to x partially. Okay, now I am saying partially because u is a function of three variables x, y and z. It is a function of more than one variable. So whenever there is a function more than one variable dependency, then we have to take a partial derivative. Okay, and at that time your y and z now constant with respect to x. So if I take a derivative of this u with respect to x, what happens here? Log is there, and we all know the derivative of log x. It is 1 upon x, right? So using that derivative here, I can write 1 upon x cube plus y cube plus z cube minus 3xyz, right? Into, again I have to take a derivative of this term which is present in logarithm. Okay, so here the derivative of this term with respect to x now, it is 3x square minus 3yz. Derivatives with respect to x, so your y and z are constant here, right? Now I can write this 3 common x square minus, we have taken 3 common, so remaining term it is only yz upon x cube plus y cube plus z cube minus 3xyz. Okay, but if you see here in the function, x cube is there, y cube is there, z cube is there, and 3xyz is there. Means all these functions in xyz are same, right? So I can write the derivatives of u similarly with respect to y. Only the change is what? Yes, this time here will be the derivative with respect to y. So now your term will be in terms of y here, and here x will here y will remove and x will come, right? So that will be the change here, right? So here I can directly write the derivative now. 3y square minus xz, right, upon x cube plus y cube plus z cube minus 3xyz. Okay, so here I have taken a derivative, and you can write the derivative of this term in numerator by differentiating this with respect to y. You will get the same value here. Okay, similarly the derivative of u with respect to z, it is what? Yes, differentiate this term u with respect to z. So similarly I can write it is 3z square minus xy upon, yes, it is x cube plus y cube plus z cube minus 3xyz, right? Now here I got all the values of u with respect to x, u with respect to y and u with respect to z. Now I can write this value adding these three together. So here now adding this together, u with respect to x plus u with respect to y plus u with respect to z. Okay, now see here, when I do this addition, if you check here, your denominator for all the three derivative is same, right? X cube plus y cube plus z cube minus 3xyz, right? So whenever is the denominator is same, we can add or subtract the numerator. But we are doing the addition. So what we have to do? We have to add all these numerators together. Okay, so taking the denominator common, I can write here x cube plus y cube plus z cube minus 3xyz, right? Now here writing the value 3x square minus yz plus 3y square minus xz plus 3z square minus xy, right? As I told you, if denominator is same, we can add numerators only. Okay. We can solve this further by taking 3 common. What is there? Yes, x square plus y square plus z square minus yz minus xz minus xy, right, upon x cube plus y cube plus z cube minus 3xyz. Okay, but here now if you see, I can use the result for this x cube plus y cube plus z cube. I have a formula. Okay, what is the formula? If there is a cube plus b cube plus b cube plus c cube is equal to a plus b plus c in bracket a square plus b square plus c square minus ab minus bc minus ac plus 3abc. This is actually the result. So using this result here for this x cube plus y cube plus z cube, what we can write, see, this will be then 3x square plus y square plus z square minus yz minus xz minus xy upon, now using the formula here, I can write x plus y plus z in bracket x square plus y square plus z square minus xy minus yz minus xz plus 3xyz. This is according to the formula, but already we are having a negative term there. What is it? Minus 3xyz. So these term get cancelled. So what is the remaining term then? Only this numerator and this denominator. So therefore, in next step we can cancel this bracket also. Okay. So here what happens? 3 upon x plus y plus z. This is only the value for u with respect to x plus u with respect to y plus u with respect to z. Okay. So using this value in left hand side. Okay. So what is our left hand side? It is dou by dou x plus, right? Let me show you. See here, this we have find here, left hand side. Okay, we have solved this left hand side and we got this value. Now here I am going to put the value for this u with respect to x plus u with respect to y and u with respect to z. So here I can write dou by dou y plus dou by dou z into dou u by dou x plus dou u by dou y plus dou u by dou z, and putting here value for this. So what I get? Dou by dou x plus dou by dou y plus dou by dou z, right, into I have a value here for this term now. Putting this value here, 3 upon x plus y plus z. Okay. Now what does it mean? It means we have to open the bracket now. We have to multiply by each derivative to this function. So here dou by dou x of 3 upon x plus y plus z plus dou by dou y of 3 upon x plus y plus z plus dou by dou z of 3 upon x plus y plus z. But if you see in the denominator, each term, each variable is of degree 1. Okay. So I can use the concept of this differentiation, derivative of 1 upon x. What is it? Minus 1 upon x square. Okay, so here if I differentiate this with respect to x, its derivative will be minus 1 upon, but already 3 is there, so I can write here minus 3 upon x plus y plus z whole square plus minus 3 upon x plus y plus z whole square plus minus 3 upon x plus y plus z whole square. Okay, and now here if you see, all the denominators are same, and whenever your denominators are same, we can simply add the numerators and we can simply add the numerator or subtract, right? But here we have to do addition. So minus 3 plus minus 3 plus minus 3. So it is minus 9 upon x plus y plus z whole square. And I think now this is our required right hand side. You can check here. See, this is our required right hand side. So this is how also you have to solve the example. You have to first of all check always whatever you have to prove, and then accordingly you have to solve the example. Okay. So I hope you all understood the example. So I'm going to write here, hence proved. Okay. Now the next example that we are going to solve, that is our now the 7th example on the same topic. Okay. So more example you solve, more ideas will be clear. Okay. Let's solve the example here. Now this time what you have to do, function is given to you. It is in x and y. So it means your function is depending on two variables x and y. Right? Dependency is more than one variable. Definitely we have to take a partial derivative. Okay. And now we have to show here uxx plus uyy is equal to 0. I told you in first lecture all the notations. What is the meaning of this uxx? What is the meaning of this uyy? There I use the notation f instead of u. Right? So what is the meaning of this uxx? It means you have to take a derivative of u with respect to x 2 times. You have to double differentiate this function u. Okay. And similarly here uyy means a double derivative of u with respect to y. Okay. I hope you understood. Let's solve the example. First of all, always write down a given part here. Okay. Given is u equal to log of x square plus y square plus tan inverse y upon x. Right? Now here, first of all, I'll differentiate this u with respect to x. Right? So differentiate u with respect to x partially. Okay. So this will give you first order derivative u with respect to x. I can write this ux, first order derivative of u with respect to x. Okay. Now if you check u, there is a log x square plus y square. So its derivative is what? 1 upon x square plus y square into 2x, right? Plus, now tan inverse is there. And we all know what is the derivative of tan inverse x? Yes, it is 1 upon 1 plus x square. Using this differentiation, I can write the value here 1 upon 1 plus y upon x whole square. Instead of x, there is now y upon x. But here again I have to differentiate this y upon x with respect to x. So this time y is constant and 1 upon x differentiation, it is minus 1 upon x square. Okay. And if I simplify this, what I get? 2x upon x square plus y square. Okay. Now this is a negative term. So I'll write here minus sign. Okay. And y upon x square. And here, if we solve this denominator, it will be y square upon x square. Right? And if I do the cross multiplication, I'll get here, yes, correct, it is x square upon x square plus y square. And now here this x square will get cancelled. So what is the remaining term? Yes, definitely you will get your value for ux is equal to 2x minus y upon x square plus y square. Okay. Now here again I have to differentiate the term with respect to x because I want a double derivative uxx, right? So now here again differentiating with respect to x, again differentiating with respect to x partially. So what I will get here? Yes, dou 2u upon dou x square means double derivative of a function that I can write uxx. But now here I have to use u by v rule because x is present in numerator and in denominator also. Okay. So if I use here u by v rule, denominator is first of all constant. Taking a derivative of numerator, it is 2 minus. Now numerator it is constant. Taking a derivative of denominator, it is 2x. Okay. And divided by x square plus y square whole square, right? Now simplify the term here. So it will be 2x square plus 2y square minus 2 into 2, that is 4x square, minus minus it is plus 2xy. Opening all the brackets and simplify the term. So here your term for uxx will be then 2x square minus 4x square means it is 2y square minus 2x square plus 2xy upon x square plus y square whole square. Okay. So say this is our equation 1. We got uxx. Similarly now I have to find uyy. Correct. Okay. So differentiate first u. Differentiate u with respect to y partially. Okay. Now partially means you have to keep this time x constant. What is our u here? This. U is equal to log x square plus y square plus tan inverse y upon x. So differentiating this term with respect to y. So here the derivative will be uy, that is u with respect to y is equal to 1 upon x square plus y square into derivative with respect to y, it is 2y plus. Now here tan inverse y upon x, differentiating this with respect to y, so it will be 1 upon 1 plus y upon x whole square into derivative with respect to y. So this time 1 upon x is constant and derivative of y is 1. Right? Now simplifying this. So what I get? 2y upon x square plus y square plus 1 upon x into. Now if I again solve this denominator and cross multiply, what I get here? Yes, it is x square upon x square plus y square. Very good. So here x will get cancelled and what is the remaining term? Only x. And if you check, your denominator is same, so I can add numerators. So I'll get here value for uy. It is 2y plus x upon x square plus y square. Right? Now here differentiating again with respect to y because we want u by y, double derivative of u with respect to y. So I'm going to write here differentiate again with respect to y partially. So what we get? Uyy means double derivative of u with respect to y. You can write dou 2u upon dou y square also. So you have to remember the notations. Okay. So again if you take y is present in numerator and in denominator also. So again I have to use u by v rule. Right. So using your u by v rule. First of all your denominator is constant. So x square plus y square it is constant. Derivative of numerator with respect to y it is 2 minus. Now this time your numerator is constant and derivative of denominator with respect to y it is 2y. Right? upon x square plus y square whole square, right? And now simplifying the terms, open the brackets here. So 2x square plus 2y square minus this 2 into 2, that is 4y square minus 2xy, okay, upon x square plus y square whole square, right? So here I got the value for u by y. It is what? Yes, it is 2x square minus 2y square minus 2xy upon x square plus y square whole square. So say this is our equation 2. Okay, now I got the values for uxx, uyy. See here, what I have to find? uxx, uyy. I got all these two values, right? Now I am going to solve the left hand side. So, and I will show here right hand side is 0. Okay, so using this left hand side, consider left hand side, what is it? Addition of this uxx and uyy. Now if you check, what is our uxx here? Right, 2y square minus 2x square plus 2xy. 2y square minus 2x square plus 2xy upon x square plus y square whole square. Now we are doing addition here. So plus, now write the value for uyy. Here it is a value for uyy that we find. So it is minus 2y square minus 2xy upon x square plus y square whole square. Okay, now see here again your denominator is same, so we can simply add the numerators, and if we do addition of numerator, 2y square minus 2y square will cancel, minus 2x square plus 2x square will cancel, plus 2xy minus 2xy will cancel, right? So here definitely you can tell the answer. What is the answer then? 0, right? So here this is our required right hand side, and we can see here, hence proved. Okay, so simple logic you have to use. Check your question and accordingly differentiate your function and solve the left hand side and right hand side to get the answer. Okay, now let's solve one more example on this. This is a very simple example here again. Here again we have to find the double derivative of a function. Function fxy is equal to f by x we have to show. Means what is the meaning of this? I told you this also in first lecture, what this notation is. Okay, this means there is a derivative of function with respect to xy. It is a double derivative and it is called mixed derivative, right? So what we have to do? First differentiate with respect to y, then with respect to x, right? And then with respect to x, and then with respect to y, and show that both the derivatives are same. This is the concept here. Okay, so function is given to us. First of all, always write down your given part. So what is given to you? F is equal to log x tan inverse x square plus y square, right? So here I'll find the left hand side first. Let me tell you what does it mean. This is a rough work I am using here. fxy means I can write here dou to f upon dou x dou y. Okay, and fyx we can write dou to f upon dou y dou x. Okay, so first of all solving this. So I am going to differentiate this with respect to y first and then with respect to x. So differentiate f with respect to y partially, because the function is of x and y. It is depending on two variables x and y. Okay, so here when I differentiate this function with respect to y, we have to keep x constant, right? So derivative of function with respect to y, keeping x constant. So your log x will be constant here, and derivative of this tan inverse x square plus y square, it is what? 1 upon x square plus y square into, with respect to y, so it is 2y, right? Now simplify the term. It is log x into 2y upon x square plus y square. Now what I have to do? I have to differentiate this with respect to x. So differentiate again with respect to with respect to x partially. Now this time y will be constant. So here dou 2f upon dou x dou y means that will give us the value for fxy. So 2y is constant with respect to x, so we can keep outside, and using u by v rule for log x and x square plus y square. So see here what I can write. First of all, your denominator is constant, derivative of log x is 1 upon x minus. Now log x is constant, derivative of the denominator with respect to x upon x square plus y square whole square. Okay, so that is a differentiation. Now we need not simplify this term, just we have to show both the derivatives are same, so keep this as it is. Okay, and now differentiate f with respect to x partially. Now this time we are differentiating first with respect to x and then with respect to y. Okay, so when I differentiate this f with respect to x partially, your y is constant, but here log x is also function of x and tan inverse is also function of x, means we have to use u into v rule. So suppose first of all I keep this log x constant, okay, and I take the derivative of tan, so it is 1 upon x square plus y square into 2x, this time the derivative with respect to x, right, plus, now if I keep tan inverse x square plus y square constant, okay, and I take a derivative of suppose this log x, so it is 1 upon x. Okay, so I hope you understood the example. Now I have to differentiate this with respect to y again. So differentiate again with respect to y, right? So this will give us double derivative of function with respect to x and y. So that will be dou by dou y of dou f by dou x, means dou 2f upon dou by dou x, that is equal to f by x. Okay, so taking a derivative, now this is a derivative with respect to y, so your x is constant, so I can write this 2x log x constant, 2x log x constant, and taking the derivative of this 1 upon x square plus y square with respect to y, so it will be minus 1 upon x square plus y square whole square into derivative of this with respect to y, it is 2y. Okay, then here for this term, okay, 1 upon x is constant, so I can write here plus 1 upon x, and taking a derivative of tan inverse with respect to y, so it is 1 upon 1 plus x square plus y square whole square. A little change in this example is there. We are having a derivative of tan inverse, right? And it is what? 1 upon 1 plus x square. So our x is x square plus y square. So it should be 1 plus x square plus y square whole square. Okay, so I have made necessary changes here in the example. Just I forgot to write there 1 plus. Okay, so here now I use that, and here also we have to make a change. It should be 1 plus, right? Now here 1 upon 1 plus x square plus y square whole square, and into we are differentiating this with respect to y, so its derivative it is 2y. Okay, now here if I find this 2y common, right, and I write the remaining terms, then it is minus 2x log x upon, what is it? Yes, 1 plus x square plus y square whole square plus 1 upon x into 1 plus x square plus y square whole square, right? This is the result after finding 2y common. Now here denominator is same, but here it is x, so I can find this denominator common, 2y upon 1 plus x square plus y square whole square, and what is remaining then? Minus 2x log x plus 1 upon x, right? So here if we cross multiply the terms, what we get then? Okay, also when we differentiated here, there also we have to write a square. Now I have made here also corrections. So when the square comes for this bracket, one term remains there after finding a term common at denominator, and when we solve this cross multiplication, see here what we get, 2y upon 1 plus x square plus y square whole square, right? And now here it is minus 2x square log x, then plus here it is 1 plus x square plus y square whole square, right? And divided by x into 1 plus x square plus y square whole square. Okay, and this we can write, yes, 2y keep as it is, so it will be minus 2x square log x plus 1 plus x square plus y square whole square upon, at denominator, 1 plus x square plus y square whole square bracket square. Okay, now this is what your differentiation, double derivative of function with respect to y x, right? And now we have to check here, are these two derivatives the same? So first of all we'll check term by term. See here, in this derivative 2y is common, yes, say this is our equation 2, here also 2y is common, right? At denominator, 1 plus x square plus y square whole square bracket square, also here 1 plus x square plus y square whole square bracket square, right? And if we see numerator, 1 plus x square plus y square into 1 by x is there, right? So I can write this term also, 1 plus x square plus y square whole square. This x I can write here 1 by x, right? And if I write this x as a 1 by x here, I have to divide by this x here also. Means I can divide by this x to this both the terms, and this x will get cancelled. So this should be minus 2x log x. And now remaining term, yes, you can check here, minus 2x log x. Means both the values fxy and fyx are same here. So from 1 and 2, what we can say? From 1 and 2, we can say fxy is equal to f by x. So from this example you must understood we have to solve examples very carefully. Small mistakes also make our example wrong. Okay, so solve the examples carefully, use the differentiation carefully. Okay. Now the next example that we have to see proves that dou 2z upon dou y square. Again here comes the double derivative of a function. Okay, so double derivative of z with respect to y and double derivative of z with respect to x. We have to find from this given function. So first of all we are going to write a given part. It is z equals to f of x plus ay plus phi of x minus ay. Now differentiating this z, differentiate z with respect to x partially. Okay, so when I differentiate this z with respect to x partially, keeping y constant, I'll get the derivative of this f dash x plus ay, and I am differentiating with respect to x, so y is constant, so its derivative is 1 only, right? Plus similarly here derivative of phi is phi dash. Okay, and it is a function of x minus ay. So when I differentiate this with respect to x, its derivative is 1. Now again differentiate with respect to x here. So this time this will give me dou 2z upon dou x square, double differentiation. And definitely it will be same f double dash of x plus ay plus phi double dash of x minus ay. Okay, say this is our equation A. Now to find dou 2z upon dou y square, differentiate z with respect to y partially. Partially means keeping now x constant. So what is the derivative? Dou z by dou y is equal to, this is our z, differentiate this with respect to y. So this will be f dash of x plus ay into derivative of this x plus ay with respect to y, it is a, plus phi dash of x minus ay, and derivative of this x minus ay with respect to y, it is minus a. Okay, now similarly again differentiating this z with respect to y. So here I am going to write again differentiate z with respect to y partially. Okay, so I'll get the derivative of z, that is a double derivative with respect to y. Now this time derivative of this f dash of x plus ay, it will be f double dash of x plus ay into derivative of x plus ay. Already there is a in multiplication, so if I take the derivative of this x plus ay, there comes again a, so that will be a square, plus derivative of phi dash of x minus ay, it is phi double dash of x minus ay. And if I again differentiate this x minus ay, that will give me minus a, but already there is minus a, so minus a into minus a, that will be a square. So I can write here a square, that is equal to a square common f double dash of x plus ay plus phi double dash of x minus ay. Okay, say this is equation B, and from equation A and B, what is the value for this double derivative? You can check. What I can write instead of this? Dou 2z upon dou x square, right? So here I can write then dou 2z upon dou y square is equal to a square dou 2z upon dou x square, just replacing the value from a. So here I can write hence proved. That is your proof for the example. Okay, so I hope you all understood all the examples that I have taken in this lecture. Thank you all for watching this video, and in next video we will see the next article. Okay, thank you.